Hello students, welcome to Soros's classes. In this video, I will be solving the following question from ISS 2017 paper 3. Now here we have to write briefly on sample size determination, cumulative total method of PPSWR sampling and Rao-Hartley-Cochrane scheme. Now let's start with the first one, that is sample size determination. Now let us consider a population having density of f dash and with mean as mu and finite variance as sigma square. Now let x and bar be the sample mean computed from the random sample of size n. So it is the sample mean computed from a random sample of size small n, from a random sample of size small n from the said population. Now let epsilon and alpha, they are two specific numbers. So if we let epsilon and alpha be two specific numbers such that this epsilon is greater than 0 and this alpha lies between 0 to 1, then if n is greater than n naught, where n naught is a function of epsilon, alpha and sigma square, and n is any integer, where n is any integer and this n naught is a function of epsilon, alpha and sigma square, then we will find that probability, this x bar n minus mu, it lies in the interval of minus epsilon to epsilon. This is greater than equals to 1 minus alpha. So if n, which is any integer, if it is greater than n naught, where n naught is a function of epsilon, alpha and sigma square, then we can find that probability, this xn bar minus mu, it lies in the interval of minus epsilon to epsilon, it is greater than 1 minus alpha. Here this epsilon, this is known as margin of error. This is known as margin of error in estimating mu by xn bar, and this 1 minus alpha, this is the desired level of accuracy. It is the desired level of accuracy. So according to Chebyshev's inequality, we have that if x is a random variable and gx be any non-negative real valued function, if gx is a non-negative real valued function, then we have probability our gx is greater than equals to k. This is less than equals to expectation of gx divided by k for every k greater than 0. So this is our Chebyshev's inequality, that is, if x is a random variable and gx is a non-negative real valued function, then probability that gx is greater than equals to k, this is less than equals to expectation of gx divided by k, where k is greater than 0. And with the help of this Chebyshev's inequality, we can prove that probability, this xn bar minus mu, this lies in the interval of minus epsilon to plus epsilon. This is the probability xn minus mu is greater than equals to minus epsilon and less than equals to epsilon. This is greater than equals to 1 minus alpha for n greater than sigma square divided by alpha into epsilon square, for n greater than sigma square divided by alpha into epsilon square. So let's prove it. Now this probability, this part, that is left hand side of this equation, can be written as probability mod of xn bar minus mu. This is less than epsilon, or this is equals to probability xn bar minus mu whole square. This is less than equals to epsilon square. Now from this Chebyshev's inequality, we can say that this is greater than equals to 1 minus expectation of xn bar minus mu whole square divided by epsilon square. So we are getting it from this Chebyshev's inequality, where as we can see this xn bar minus mu square, it is a non-negative real valued function. So from here we can say probability xn bar minus mu whole square, this is less than equals to epsilon square. This is greater than equals to 1 minus sigma square divided by n into epsilon square. Since now why we can write this, because this expectation of xn bar minus mu whole square, this is nothing but our variance of xn bar, which is equals to sigma square by n. So we get our probability xn minus mu whole square is less than equals to epsilon square. This is greater than equals to 1 minus sigma square by n into epsilon square. Now if we compare this equation, suppose we name it as equation number say star and double star, and this one as our equation number, this one as our equation star. So by comparing the star and double star, we get, so from star and double star we get this 1 minus sigma square divided by n into epsilon square. This is greater than 1 minus alpha, or our n is greater than sigma square divided by alpha into epsilon square. So this would help us in determining the value of n, that is n is greater than sigma square divided by alpha into epsilon square. Now if we use the results on the confidence interval of mu, that is, we know if we use the fact that the maximum margin of error in estimation of mu corresponding to 100 into 1 minus alpha % confidence interval interval. So if we use the result that the maximum margin of error in estimation of mu corresponding to 100 into 1 minus alpha percent confidence interval is z alpha by 2 into sigma by root n, that is probability mod of xn bar minus mu, this is less than equals to z alpha by 2 into sigma by root n, this is equals to 1 minus alpha. So if E is some specified margin of error, if E is some specified margin of error in the estimation of mu, so that we have at least 100 into 1 minus alpha percent confidence in the accuracy of the process, then we can write, so if E is some specified margin of error in estimation of mu, so that we can have at least 100 into 1 minus alpha percent of confidence in accuracy of the process, then we can write probability mod of Zn minus mu is less than equals to E, this is greater than equals to 1 minus alpha. Then we can have this z alpha by 2 into sigma by root n, this is less than equals to E, or this would imply our n is greater than equals to z alpha by 2 square into sigma square divided by E square, where this E is some pre-assigned quantity, So with this formula we can find, or we can determine the size of sample, that is we can find the value of n. So we have completed this first one, that is sample size determination. Now the next two would be done in the next video.